Next episode.
All right, welcome everybody to a new edition of Next Episode, the podcast that talks about sustainable technology solutions. Today we are joined by Fabio Ferrari. Welcome, Fabio.
Thank you, welcome.
You are the head of circular carbon and integrated solutions.
Yeah, correct.
That's a mouthful. You are a chemical engineer by background.
Yes, I am. I studied here in Milan, and I have also an MBA in the Bocconi Business School.
Okay. And a lot of experience in the chemical industry then, I assume.
Correct. I had more than 20 years. I worked first as an EPC contractor.
Okay.
And then I moved to licensing, doing all the stuff connected to syngas production and chemicals production. And then I decided to join NEXTCHEM just for this challenge about CO2 management. That seems something like a very end of the process, but it's something that is very important because this is interconnecting different processes and provide solutions to problems that in any case we have to solve.
Okay, so the challenge is what drives you to NEXTCHEM.
Yeah, challenge is for sure that, and then the technical possibility to see many different technologies. In NEXTCHEM we have so many, so even a small challenge like that becomes something like a very good experience to see all the different prospects in the company.
Okay, and today we're going to talk about carbon management. I think if you look at, of course, carbon management is the big issue of this century. How to manage greenhouse gas emissions. But I think carbon in the air, what we breathe in every day, is like I looked it up, is 0.04%.
Well, let me say that CO2 is what really brings life to the earth. That's the real source of that. Without CO2, we would not have something normal, conventional life. And then there's been an evolution that the impact of human activities have been now changing the concentration of CO2. So we want to be compensate on that somehow with technology, and in order to avoid that our industries are somehow affecting the general climate change that might be happening.
Okay, so then I think carbon management or carbon capture, I think, is a thing of the past, I think already decades. I think the first technologies are a bit older, and then
carbon capture, let me say, CO2 by itself is something that coming from the normal combustion processes in other process. So as every time we say, even if it's a little technical, entropy is the reason why CO2 is emitted by the processes. Okay. And in the past, the CO2 has been, in any case, a possible molecule that can be used, for example, for producing urea. So it was something, an element of attention in the past for a different reason. So solutions have been implemented also in the past in order to try to capture CO2 with a different
as a feedstock.
As a feedstock, or in the case to remove that from syngas, for example, pre-combustion in ammonia plants has always been seen something like a solution to remove CO2 from the syngas to produce then something like ammonia, for example. Okay. And then in the process, you can use, as I was saying, CO2 for producing urea. That's fine. And in the past, that was a real challenge, capture CO2 in order to use it. Now, the quantity of CO2 is so big in the industry that we have to implement solution in order to try to remove this concentration in the air. So some solution can be very complicated, like direct air capture. So that means that you try to directly take the CO2 from the air and then convert it to use it or somewhere else.
So carbon management, I think the direct air capture is capturing the 0.04% out of the normal air and do something with that either.
That's the point. This is something like more an environmental challenge, which is, let me say, not really our focus, because in NEXTCHEM, the real idea is to try to manage the CO2 in the processes we have and then to find solution in order to manage the same. That's why it's no more only carbon capture by itself, but it's carbon management. That means the possibility to manage all the value chain of the production, including also the emission, and in that case, of course, the CO2 is part of that.
Is it viewing carbon as something that has value?
It can be. It can be, depends on let me say the CO2 we are actually emitting in the industry is very high. So the point is that we cannot imagine to convert all the CO2. but somehow we can try to find a solution in order to limit the quantity we are emitting, maybe valorizing part of it in order to compensate or economically in order to make the project viable and to have a solution for the client to implement, mitigating the impact of implementing something that is somehow expensive like carbon capture is.
Okay, so carbon capture, I think, is a very high, very expensive, probably very energy intensive. What are good ways to capture / manage carbon? How do you do that? Probably depends on the process where you're capturing it from.
Yeah, it depends from the process. The real advantage is that in NEXTCHEM we are so competent, we have so large experience in doing such type of processes for different reasons. In the past, as I was saying, to, for example, capture the CO2 in order to reuse it in ammonia in the urea plant. The idea is to take all those experiences we have had in the past and to really implement the same, to try to optimize the system itself. So when you have something that is mandatory for environmental reason, the possibility to optimize the system, to find solution that can be used and integrated inside the process itself, mitigating the impact for the client, is where we can really play our role.
Okay.
And this is coming because nobody, or most of the people does not know that MAIRE Group has about 30% of the market share of built post-combustion carbon capture plants.
Okay.
Which is really something astonishing if you think about that. That means that 1/3 of all the CO2 that is captured in post-combustion, it is coming from MAIRE Group.
Well, I also did not know that. So, but then let's focus on that first. Post combustion. How does that work? Something is burned inside a reactor. Depends on the process. Then.
Yeah, let me say. Typically, is in all the processes, most of the processes we have, there is somehow some combustion somewhere. So then we have some flue gas that is emitted to the atmosphere, and around 8 to 15% of this flue gas is CO2 by itself. Mm-hmm. The point is that in post-combustion, because it's already combusted, and it is a particular flue gas, it's very rich in oxygen, so it's much more complicated to manage that. So, for example, to make a comparison, even if it be little technical, pre-combustion are normally cleaning up CO2 from syngas, so there is no oxygen. So it's much more lean and simple. You are at high pressure, so high partial pressure means a higher possibility to be captured, easier to be done, and lower energy to then restore the solution that you're using in case it's an aminic type. In post-combustion, you are low pressure, high concentration of oxygen, and very large quantities of flue gas, so a very high stream of that you have to treat. The possibility to implement solutions like aminic solutions is to wash that stream, to use the absorption of the aminic solution to capture the CO2 molecule. Then all the rest, like nitrogen and oxygen and all the other components, would be released to the atmosphere, but it will be clean.
Okay, so how does that work? You say the amine solution, that's like a sponge? Or can you try to explain this for a non-technical person?
Let me say is somehow is like when you're in your blood, you're taking the molecules with the what you have inside the blood in order to move that around. Is a contact between a gaseous phase and a liquid phase. The liquid phase is the amine, and then there is this chemisorption process where the CO2 molecule is attached to the amine. And it can absorb that. And then this fluid, which is a liquid form, is going away, enriched by the CO2. And then the gaseous of the rest, which is not, let me say, interacting with the liquid, is going to the atmosphere.
If the comparison that comes to my mind in, let's say, in a household situation, is it like dissolving some sugar in your tea?
Oh, well, it's not exactly the same because this one is a different type of solution, but it's like really you have those amine system that chemically is bonding selectively only on the CO2.
Okay.
So is identifying the CO2 in the system, let me say, is taking it and then is bringing away it from somewhere else. Okay. And then the energetic impact of that is that then you would like to have a loop, so to recycle back this aminic solution, you need to remove the CO2 from the solution. To do so, you need to heat up. And that is where the impact in terms of energy comes from those type of solutions. Okay. So you have to heat up. You say you strip it, so you go with that temperature. The CO2 is removed, separated from the solution. The solution is now clean, it's recycled back. But then you have the CO2 that is pure enough to be sent downstream.
Okay, and to what let's say we started with the 0.04% in general air, then how pure is that stream?
Okay, then when you have one side, you have nitrogen, which is not affecting nothing, it's cleaned up. The CO2 then is very concentrated. It is something like, can be also 99%.
Okay.
It might be containing some oxygen, some water, of course, because you're washing with this solution. But then, depending on the process, you decide you can somehow purify that. And again, we have our experience in order to be able to purify those to reach the highest purities to be fed for processes like urea, for methanol production, or in some cases just to put them in a pipeline, as we did in Casabossetti project, where we were capturing the CO2 for a very complex stream that was let's say from a gas turbine, and then we need to clean it up to send in a pipeline to be sequestered in the Mediterranean Sea. And this has been the first project in Italy doing so, to sequester CO2 after a post-combustion capture.
But then you send it off as a gas, or is it a liquid then?
In this case, it's a gas.
Okay.
And this is an alternative we can again provide to clients, because if you have a pipeline and you have the possibility to directly send it somewhere and you are going to use it or sequester it, you can keep it in gaseous form. You just need to qualify to reach a purity for that. If you have instead a problem of logistics, because maybe the site for sequestration is very far abroad, or you have some off-take, some user stuff very far, to transport CO2 in gaseous form is much more complicated. It's a matter of volume. So if you have a very large gas, you need a lot of volume to move it. Liquid form is much more smaller in terms of volume. So a solution can be to liquefy that. And again, this is providing an opportunity for the company, because we have this technical problem. How can we provide a solution for the client for liquefying CO2? If you go in conventional market, normally the quantity is very limited, only for making some gaseous water with the gas. You can then liquefy that in small capacities, and you have some solutions that are tailored for that. But if you go very large, and we are speaking about industrial plants, where it might be 5, 7, 10 times the conventional liquefaction units, you need to implement different solutions in order to achieve that target and optimize, of course, the CapEx and the OpEx of the system. And in the past, we discovered that in MAIRE Group, in NEXTCHEM then, we have a strong experience in cryogenic solutions.
Okay.
So the idea has been, why not implementing our own technology in order to make liquefaction? And then we have this new technology, which is called NEXTCHEM, that is liquefying the CO2 for large capacities, using CO2 itself as a refrigerant. Because in the past, maybe not technical people might be not knowing that, but instead of using very complex hydrocarbons for making the frigories to make cold, you were using CO2. Then it was less efficient.
You're using CO2 to cool CO2.
In our technology, yes. In the past, we were using CO2 just to cool other systems. But then comes some hydrocarbon that will be much more efficient in some cases. But if you don't want to use hydrocarbons in your plant, because maybe you don't have it, you don't want to purchase it, you have already CO2, why not use the characteristic of the CO2 itself, the thermodynamic of the system, in order to use it to cool it? And this is our technology that is providing this opportunity to reuse the system, be much more lean in terms of complexity, and also having the possibility to achieve the possibility to have the economy of scale for very large plants, overcoming all those limits from the past.
So let me recap a bit. You mentioned very briefly NEXTCHEM is a liquefaction that uses the hydrocarbons to cool down.
No, it's not using hydrocarbons.
Okay, as a refrigerant.
Yeah, it's using CO2 itself. So very technical, but you compress CO2, you flash it, you have some cold, you use it to cool it down, and then at the very end you have a part of that will be liquid. You can offtake and manage, turn it into boats, to trains, to move it far away where the place of the industry is. And this stream of opportunity does not, let me say, close the opportunity to go for other technologies. So we can couple that one with the absorption carbon capture, that is post-combustion or pre-combustion, but can also use it for revamping, where you have some process where you have CO2 and you want to move it somewhere else. You can think about in future that will be needed to collect all those CO2 that will be captured somewhere and then move them those streams somewhere else. And this is the hubs in the future that will be present in order to move CO2 all around.
It sounds a bit like you're creating now I think there's a let's say water as a feedstock, but now also CO2 more as a feedstock, as something that has value in location A, maybe not so much in location B. And how do you transport the value? How do you make it efficient? How do you is that a correct assumption?
Somehow I see. Yeah, let me say CO2 is very large in quantity, but as I was saying before, part of that can be reused. You can use it for enhanced recovery, so you can send it underground in order to push on top the case. You can use it to convert it to methanol, for example, in future. You can use it again for making urea. You can use in some cases also for pharmaceutical environment, for food grade. So it can be partially also a value. It is maybe not totally, of course, so there will be some solution for sequestration, for sure. But somehow we can, let me say, make it something that can be somehow managed. That's the reason why the CO2 management is no more CO2 captured by itself.
So are there particular, because there are many, I think let's say the typical hard to abate sectors is steel, of course, fertilizer, cement industry. Does it matter where it comes from or where you use it, or you can be adaptive to fit whatever a source is?
We can be, let me see, the real point about carbon management is that you need to tailor the solution for each industry. So, for example, we were mentioning now the case of for conventional absorption technologies that are, let me say, very useful for very low concentration of CO2 in the flue gas stream. But if you think, for example, of cases in the industry where the concentration is much more higher, and maybe you do not have any spare heat you can use for regenerate the solution, that is where you can implement different solutions. No more absorption can be cryogenic solution without liquefying at the very end, but that using the cryogenic properties of CO2 to be condensed and separated from the rest of the stream.
Okay, that's quite a lot of information. So the cryogenic, you cool it down to make it a liquid.
Yeah, so for example, imagine you have a very large stream of gas with many different molecules.
Yes.
And the only one that is going to condense is CO2. So if you put it down the temperature, the CO2 first, you have to remove water, then the CO2 start to condense. And then once it's condensing, you're separating it from the rest.
So you move the temperature towards the condensing point of that specific gas, in this case CO2, and then it becomes a liquid. You can take it out.
And the rest is clean for the very same reason. Of course, you cannot do that, let's say, simply. You have to make some additional implementation. This is where our technology that is called Annex CryoCool, it is implementing this solution. Why I'm saying that? Because the point is we do not have a single solution for all. We have multiple solutions, many different options. You can select and decide, or we can agree with the client to assess their situation and try to tailor their solution for CO2 removal. That's the point. And then also manage the logistic of that. The real point is that it would be an end-to-end solution. So we have all the experience of KT for steam reformer, for example. We can attach our systems to the existing asset. So for example, a stack where the flue gas is going away. And we have the competence to ensure that there is no impact in the existing asset. Then we can provide any solution, depending on the case, tailor the same for the client, recovering the heat if necessary, electrify, we don't have heat available, and then also delivering the CO2 at the condition the client is willing to have, or the off-taker is able to take it. So it can be in liquid form, in gaseous form, purified as much as possible.
How energy intense is all of this?
Well, it is true that for doing so, is not for free. You need to spend some energy, whether it is available spare heat or you have to have electricity to do so. The real point is that, of course, that's the reason why CO2 management, the possibility of partially reutilize that will be mitigating in this impact in terms of CapEx that you have to put and OpEx you have to spend in order to make the system work. The real point is that for sure in future, nobody is willing to have a totally uncarbonized system, so some solution should be implemented. So when you are in the direction to be removing this CO2, to find solution that, you need to try to mitigate that, optimize the system, minimize the CapEx, minimize the OpEx, and provide a solution that is already complete enough to make the client sure that there is no effect before and there is no impact downstream.
And I can imagine that, because there's this cost, capex and or opex. To what extent is this pushed by regulators? Because there's the carbon management, carbon border adjustment mechanism. I love the word.
Yeah, CBAM is
CBAM,
most simple.
yeah.
Yes.
But those type of, I think mostly European, but I think other regions in the world are following a similar approach, and not everybody at the same pace. But is this the future? Is the regulation needed in order to make this work?
Yes, for sure. The regulation is important in order to have something like a common benchmark for everybody to be playing the same rules.
Mm-hmm.
My point of view, and I believe the point of view of everybody, is that in any case, as I was saying, we need to implement solution for carbon capture, because we cannot continue to emit as we are doing now. The point, like in the past, we were also emitting some pollutants that now we are normally removing. We are thinking about the cost as well to try to minimize the impact of this pollution. CO2 is part of that. So solution will be implemented. It's a matter of decide how fast going in the direction of decarbonizing, increasing.
Okay.
Maybe not being dogmatic in saying that should be totally green immediately, because you need steps in order to implement that.
It's a transition.
And, yeah, exactly. It's a transition. So you cannot say tomorrow you have to totally decarbonize. Will be not be you're immediately affecting the production. So everybody will be not willing to implement. So if you make something like a virtuous system, so like the one of CBAMs you were mentioning, is very good from my point of view, because you are stating that in Europe we have decided by definition that we are not accepting anything that will not be somehow decarbonized.
Mm-hmm.
And this is changing the mindset not only internally in the market, but also outside. So you may think that in India, for example, they are starting to think to find solutions somehow, because if they are willing to sell products to Europe, they need to implement some solution. And the mindset is changing by itself. Nobody's now, for example, would not be willing still to emit, some H2S, which is very critical for acid rain. Nobody's willing to, buy products that are not ethic enough. Nobody's willing to buy products that are not green, in the sense that they are somehow taking care about the environment.
Yeah, it needs to be part of the consideration.
Correct. So in future, you need to be, of course, providing solutions. We have them. We need to have a good pace for implementing, so a reasonable one, and then provide a general statement. This is the direction where we are going.
What I think I hear you say is the technology is here. Mm-hmm. We just have to make it work.
The technology is here. We need to decide that we are willing to implement that.
Okay.
Like, as I said, if you think about the 70s, they say our industry was not very environmental friendly. Yeah. We were emitting everything. Nobody was putting something like the SCR on the top of the stack to remove all the pollutants there. Now is something like a regulatory mandatory requirement. So you have to implement that. Now the point is that we don't have this necessity to go so fast in order to implement that, considering the capex intensity of the system itself. Mm-hmm. But in any case, we need to provide the reliability of the system in the economy itself to ensure to the producers that they have to go in this direction.
Okay.
Then we have in NEXTCHEM enough experience to demonstrate that technology is already available. We are able to guarantee that we can proceed in doing the processes and the projects, implementing them without any impact in the process itself and in the upstream asset. And then to be minimizing in terms of OPEX and CAPEX, the system itself.
So it's basically the thing that's going to really push this is just carbon pricing.
Yeah, it should be a general statement of this direction. The rules should be clarified for everybody, not only, let me say, making very strict rules in Europe, but outside Europe, nobody cares. This is something. Or the complexity of the system somehow is also how the incentives works. In Europe, we have a system. In Denmark, we have another one. In UK, we have another one. So to navigate through this, of course, it becomes something like complicated. Yeah. We need to have something like a very simple statement. This is the general way to go. We need to find solutions. Let's implement them. Maybe project by project, country by country. But in any case, we have this direction. So even if I've seen a lot of projects that are moving forward because everybody is waiting the other to see, because they don't want to be the first movers in most of the cases, sooner or later we come to a point where we do need to have them. And the advantage of NEXTCHEM is that we have already a heritage on that. We are playing our role actually, and we are ready for the future when everybody will be willing to do so.
Yeah, I think then also you have a lot of different other technologies where you can integrate with, right? So the integrated approach probably is beneficial there as well.
Correct. That's the reason why having so many technologies, so many components, we can be somehow always find a solution that is optimal for the specific case.
Yeah. All right. Any let's say final thoughts on this topic? Where do you think this is? Or you've already given a flavor of where this is heading towards, but is there any breakthrough that you think, if this happens, then?
Well, let me say, up to now, for sure, my point of view is that we need to find a solution for the electricity problem that we have now. Some projects are now stopped by the electricity availability. So the real point is that we need to be much more, let me say, optimizing our grid, because electricity is for sure one of the elements with which you can somehow allow for the decarbonization. So let me say, as soon as we are burning something, there will be some CO2. So to minimize the burning, you need to have so much more electricity and should be much more green as much as possible. So we need to find those type of solution. And once we have, let me say, high availability of let's say electricity, we can be implementing much more project for electrifying parts of the processes to produce some hydrogen for converting CO2 back to something else like SAF, like methanol. And all those will be providing much more wider opportunity in terms of decarbonization.
Okay, so the future is electric.
Somehow, for sure, yes. Will not be totally electric. This is, let me say, again, not to be dogmatic. Electricity is for sure a very good route in order to implement more decarbonization, also in processes where maybe electricity cannot be fully implemented. So we should not be saying only electric, otherwise it will be too much, but a good balance in between different technology, always in the direction to reduce or remove the CO2 carbon footprint. This is the solution from my point of view.
It's a true energy transition.
Yeah, exactly.
Thank you so much for your insights. And
pleasure.
Also a big thanks for all our listeners. If you like this type of content, please subscribe to whatever platform you are listening to this podcast on. We are on YouTube, on Spotify, on Apple Podcasts. So I hope you tune in to the next episode as well. Thank you so much.
Thank you.